Welcome to the next video on logarithms. We'll briefly review what we've done so far. We found out that when we write a number as an exponent, that exponent simply means how many times you multiply the number by itself. So 3 times itself 5 times is written as 3 to the power of 5. When we multiply numbers with the same number base, we add the exponents. So 7 squared times 7 cubed gives 7 to the power of 2 plus 3. When we divide numbers with the same number base, we subtract the exponents. So pi to the power of 9 divided by pi to the power of 4 gives pi to the power of 9 minus 4. Adding exponents only works when you have the same number base. So whilst 2 to the power of 2 times 2 to the power of 5 gives 2 to the power of 7, 2 squared times 3 squared can't be written as a simple power of either 2 or of 3. Subtracting exponents only works when you have the same number base. 2 to the power of 5 over 2 to the power of 2 is 2 to the power of 5 minus 2, but once again 2 to the 5 over 3 to the power of 2 can't be written as a simple power of 2 or 3. Any number raised to the power of 0 equals 1. 3 to the power of 0 is 1, pi to the 0 is 1, 0.7163 to the power of 0 is 1. And finally, the rules don't apply if the number base is 0. So, whilst 3 to the power of 0 is 0, 0 to the power of 0 has a rather contentious meaning which we're not going to go into, and 0 to the minus 1 again has a rather contentious meaning. It could equal infinity. We're not going to worry about that. So the rules do not apply if the number base is 0. At the end of the last video we asked, what does it look like, as in, what do our data look like? We had a series of powers. In this case we were using the number 2, and we had 2 to the power of 4, 3, 2, 1, 0. And the question was, what does this data look like? The way to answer that question is to draw a graph. On the x-axis we have 2 to the power of 0, 1, 2 and 3, and on the y-axis we have the result. Our first number is 2 to the power of 0, gives me 1. The next number is 2 to the power of 2, which clearly gives me the number 2. The next number on the list is 2 squared, which is 4, and the final number on this list is 2 cubed, is 8. And that gives us this very distinctive upward curving graph. At first sight this seemed like a rather unremarkable thing to do. Then you look at the graph a second time and you realise this is asking a very strange question. Previously we defined our power series as whole numbers multiplied together. Now that we've drawn things on a graph, we can legitimately ask a question such as, what's 2 to the power of a half? This is simply yet another mathematical instruction, and it's telling us, in this case, that instead of looking at a whole number multiplication, we have got some sort of a fractional multiplication in here. And that fractional multiplication is defined by the line on this graph. All we need to do is write out 2 to the power of a half multiplied by itself, and using our previous rule that when you have the same number base, if you multiply numbers together you simply add the exponents, we can work out that 2 to the power of a half multiplied by 2 to the power of a half must equal 2 to the power of 0.5 plus 0.5, which is 2 to the power of 1. In other words, we've found that 2 to the power of a half is actually the square root of 2. In most of life we're used to the idea that we would have 2 of something times 3 of something else multiplied together gives 6. With square roots we're asking the question the other way round. We're given a number such as the number 9, and we're saying something multiplied by itself equals 9, what is the something that we multiply together? In this case the answer is very simple. 3 times 3 equals 9. So in this case 3 is the square root of 9, and we write that out as being the square root of 9 equals 3. This now raises the question of how we interpret all of the other numbers on this line. How would we interpret 2 to the power of 1¼ or 2 to the power of 2½? Let's take 2 to the power of 3 over 2. I would interpret that as 2 to the power of 3, which is this part, and then I would take the square root of the result, which is the 1 over 2. So if I rewrite that, I can understand it as being two instructions, one after the other. The first instruction is going to be 2 squared, and then the next instruction is going to be 2 to the power of 1/2, which is obviously 2 to the power of 0.5, or the square root. If I had a more involved fraction, if I had 2 to the power of 5 over 3, I would understand that as 2 raised to the power of 5, and then I would take the cube root of that, where the cube root simply means a number which, when you multiply it by itself 3 times, gives you the number that you want in the first place. I can apply that to very, very involved fractions. I could have 2 to the power of 355 over 113, and that would mean 2 to the power of 355, and then find a number which, when you multiply it by itself 113 times, gives you 2 to the power of 335. I understand that I'm pulling an interpretation out of the air without any explanation. If this explanation is correct, then taking 2 to the power of 5 over 3 ought to give me exactly the same answer as taking 2 to the power of 5 first, and then finding the cube root of that answer. So let's try that calculation. 2 raised to the power of 5 divided by 3 equals 3.17, etc., etc. We'll put that in the memory. What we'll now do is the same calculation in a different order. First of all, we'll take 2 to the power of 5. And that gives me 32. And then we will find the cube root of 32. And if this equals this, I should find that this number is the same as the previous number I calculated. So I'll hit the memory readout, and this number shouldn't change. I'll repeat, this is not a mathematical proof, but it's a demonstration that we can understand the other numbers on the line on this graph in a relatively simple way. In the same way, we'd understand 2 to the power of 2.5 as being 2 to the power of 5 divided by 2. 2 to the power of 2.5 equals 2 to the power of 5 over 2. And if you work out 5 over 2, you'll find that equals 2.5. So that would become 2 to the power of 5, and then 2 to the power of 1/2 is the square root. So 2 to the power of 2.5 would be the square root of 2 to the 5th. At this point, it's important to point out that this sort of interpretation is done only to explain what the numbers mean. This is not the way that your calculator or your mainframe computer or your laptop or any other computer generally tends to be programmed to work out numbers. There are far more efficient ways of carrying out these calculations, but in terms of understanding what these numbers mean, this provides a relatively simple and correct understanding, even if it's not how computer algorithms actually calculate powers. So what we've done in this video is go from the idea of powers as being whole number multiplications, for example 3 multiplied by 3, or 7 times 7 times 7, where we have a whole number of numbers, to having fractional numbers, where we can have a number to the power of 7.185932 or e to the power of pi. And it's these fractional powers and their meaning that are at the root of understanding how logarithms work. In the next video, we'll start doing some practical calculations involving logarithms. We'll use fractional powers along this line to do our calculations, and we'll discover how using those allows us to do calculations such as 2 multiplied by 3 as powers, a calculation we were previously unable to do. See you in the next video.